Right, hello, welcome to the next video. As you can see, we're moving on to something new now, okay? So we're moving on to the final topic, and that is dynamics and space, okay? Space is fairly obvious what that's going to be about. That's what we'll do last. Dynamics is basically anything to do with movement. So we're going to be doing speed and vectors and scalars, displacement, things like that, okay? And we're going to start off fairly simple with something we should at this point be very familiar with, but it's a really core part of dynamics, so we still need to cover it, okay? And that is the idea of speed, distance, and time, okay? So I know that by this point, you all know the equation for speed, distance, time, okay? We've got distance equals vt, where d is our distance, v is our speed or velocity. We'll talk about that more in the next video on vectors and scalars. And t is our time, okay? And quite often we need to rearrange these, okay? And so to do that, we use a triangle, okay? In the top, we have D, and then we have V and T, okay? And then you should know by now how to use these. If we want to work out distance, we cover that up, and that tells us, well, we've got V next to T, which means V times T, because remember, in our little triangles, when they're next to each other, that means times, okay? Then if we were to cover up V, because we were working that out, we'd have D over T. And remember, if it's one on top of the other, that means divide, okay? And same, covered up T, that would give us D divided by V, okay? This should be very, very familiar to you by now. You've done it a lot in third year. We also use this equation in the waves topic, okay? So we're not actually going to do any worked examples with this equation, though we'll be setting you some questions to do yourself, okay? Now, we're going on to a different topic now, so we're not thinking about distance, speed, time in terms of waves. We'll be thinking about basically two kinds of speed at the moment, okay? And so the first one of those we're going to deal with is what we think of as average speed, okay? And that's mainly what we've used before when we've worked things out in equations and calculations, especially in S3, okay? And average speed is the total distance travelled over the total time taken, okay? So it's that equation, okay? It's your d equals vt equation, but it's handy in that it gives us an overall impression of a journey, okay? And this is what we'd use it for, journeys, okay? So say your average speed when you're driving somewhere is 50 miles an hour and you're driving for 2 hours. Well, that allows you to work out, okay, I'll go about 100 miles, okay? It's good for things like that that happen over a long period of time, but it doesn't tell the whole story, okay? Because are you actually traveling at 50 miles an hour for that whole time, okay? No, you're probably not. And average speed doesn't account for that, okay? Average speed is just telling you what your overall speed was, okay? The other type of speed we want to be thinking about is instantaneous speed, okay, which we haven't really dealt with before, okay? So the speedometer on a car is an example of something that gives you an instantaneous speed, okay? That's changing all the time. It's not measuring your speed over the whole journey. If you put your foot down, that speedometer is increasing because your speed is increasing in that particular time. If you brake, the speedo goes down because your speed is slowing down in that particular time. Okay? So yes, examples of instantaneous speed. Okay, bullet train up there. You're at that instant going 165.5 miles per hour. You're probably not going that speed the whole time. Okay? Now, we have to think about why would we want to know instantaneous speed and not the average speed, okay? But first, let's just make sure we fully know what the definition of this is in case we're asked. Instantaneous speed is the speed at a particular moment in time. It is not the speed over a whole journey, okay? It's the speed at that moment, so it's probably changing quite a lot, okay? And that's why we use it, because it's changing quite a lot, okay? Like I said before, average speed is fairly good for estimates and working out journey lengths and things, but it doesn't paint the whole picture. So let's look at an example of my average speed when I'm off to work. Now this is a bit out of date, so this was before living in Strontian, but same thing applies. So Average distance, about 38.5 kilometers, takes about 45 minutes. We change both of those into meters and seconds, and then we can work out the speed, okay? And that would tell us that my average speed on my way to work was 14.3 meters per second, which is the same as 31 miles per hour. But I'm not going at 31 miles per hour at all times, am I? Okay? So it doesn't give us that detail of what's happening in these little bits, which is why quite often it's a good idea to do both, okay? For example, my instantaneous speed while I'd be waiting at the ferry, that's 0 miles per hour. I'm not going anywhere. My instantaneous speed on the way to Strontian on the nice straight bits of road is probably about 60 miles an hour. Okay? And so instantaneous speed then is used because it gives you a more accurate idea of what's going on at any particular moment. Okay? And we need to know how we could work that out. Okay? So we'd use the same formula as average speed, but this time the times we're measuring and the distances we're dealing with are much, much smaller. Okay? So we'd be measuring times in like milliseconds. Okay? And distances would be much smaller because we're not covering very much distance in those milliseconds, okay? But it would be the same formula. Now, if we were in the class, we would do an experiment for this, okay? And I will put up a video of Mrs. Patterson talking about that experiment because it is something you can be asked about, okay? And so, there's some things we'd have to take into account though. If you were measuring the average speed, say I sent you out to the Astro and I told you to run the length of it, using a stopwatch would be fine. You can't really use a stopwatch for instantaneous speeds because the results would be inaccurate. We're talking about things happening so quickly that you can't react quick enough to press the stopwatch, okay? And so we'd use an electronic timer to eliminate our mistakes with a stopwatch, and we don't need to worry about reaction time then as well. So this might be familiar to you from last year. Some of you will have seen this before, okay? And so we do this experiment a few times, see how accurate we could be. And this is the piece of equipment we would use, okay? It's called a light gate. So how this works is it shines basically a laser we can't see between 2 points here, okay? And then what happens is we throw or slide something through that, and you might have it as being like a little cart you're putting through, okay? When you put this on the air track or down a slope, okay? And then on the top of it, you put a piece of card, okay? And then you'd have a little piece of this card sort of sticking up like this, and that little piece of card would go through there and cut through the laser, okay? And so that laser would be connected up to a computer, and as soon as this little bit here cut through the laser, it would start a timer while the laser was stopped, and as soon as that bit had passed, then it would stop the timer, okay? And then we use the distance here of this little mask and the time it was actually going through the laser to measure speeds just at that moment as it's passing through it, okay? And that lets us get really accurate instantaneous speeds, okay? So you may have to explain the steps to do this in a question, okay? So this is the steps in a wee bit more detail, and like I said, they will be gone over in the video I put up of Mrs. Patterson as well. So you connect the light gate to the computer, and measures the time when the light beam is interrupted. The distance travelled by the trolley in this time is the length of that single little bit of, we call it a mask, what we put on it. So the distance travelled is the size of that mask that's cutting the light beam. Okay, measure that with a ruler, release the trolley, let it go, note down the time the computer states, and then you're calculating it using your equation. Okay. Now, as I said before, I'm not going to get you to do any worked examples. Not in this anyway. I'm going to get you to try some problems just to refamiliarize yourself with this equation. And the key bit here is that you know the difference between average and instantaneous speeds and why we would use them. Okay? If there's anything you didn't understand here, or you're having troubles without a worked example or anything for the questions, just get in touch with me. Okay? Right. Thank you for listening, and I hope that was all understandable.